All right. Hey, welcome back, Calculus 2. Today we are going to find arc length. I've got a curve drawn here, and what I want to know is how long is that curve? And as I'm looking at this, I have to tell you, I am really not even sure how I'm going to do that. So let's not do it. Let's do something different. Let's do this one. How long is this curve? Well, this curve is going to be a whole lot easier because it's a straight line, right? And if this were on a coordinate plane, it'd be a lot easier for us to kind of picture this and imagine it. But if I've got a line that's going at an angle, I can't really put a tape measure on it and measure it like that and just estimate it. I can't measure it like that. But what I can do is use a right triangle to figure out the distance of that line, right? And we know this. This is Pythagorean theorem. So we've got A and B and C, and we know that the Pythagorean theorem says A squared plus B squared equals C squared, right? So for example, now this is not going to be to size, but let's say that this is going to be, or it's not going to be scale. Let's say that this side is 5 and this side is 2. Then we just know we would take 25 squared plus 2 squared, and we would take the square root of that, right? So I don't even know what that is. Going to be some number. Let me figure that out. 25 squared is 265 or 625 plus 4. So this is going to be the square root of 629. That's going to be the distance of that curve, or in this case, this line. Well, let's see if we can use that same type of thinking to actually figure out the distance of a curve. All right, now, if we were to just make one gigantic triangle right here, that is certainly not going to be accurate. So what else could we do? Well, what if we would make smaller triangles? What if we would make a triangle right here and figure out that segment? Now, without a doubt, that segment is going to be much, much more accurate than our first one. And this follows the thinking that we've been using all along, that when we were finding area, when we were finding volumes, that if you're doing the whole thing all at once, it's going to be really difficult. But if we break this up into tiny segments, we can actually figure this out. So let's take a look at that. So let's use this triangle that we've got there for the Pythagorean theorem, and this is going to be A, and this is going to be B, and this is going to be C, right? And we know that to find this, we have to take A squared plus B squared, and that's equal to C squared. So we need to take the square root of that, and that will give us what C is. Okay, well, let's look at this. Now, I really don't know what the length of A is, but for right now, let's just say that it's 1, okay? If A is 1, let's just assume that. Now, what is B going to be? Well, let me see. I'm going to just draw this triangle over here so it's a little bit easier to see. If this is 1, what would that be? Well, let's think about some things we know. What do we call it, like in a graph, when we go over 1 and we go up a certain amount? So if you go over 1 and up a certain amount, maybe you're used to saying it going up a certain amount and over 1. Maybe that sounds more familiar. If you go up something and over 1, what is that called? That's called the slope, right? That's called the slope. So I know that if we go over 1, whatever we go up, this number right here, our B, is going to be our slope. Okay, that's our slope. Now, how can we define slope? Well, slope is rise over run, or the change in y over the change in x. Maybe let's write it like that: the change in y over the change in x. Okay, that's what the slope is. maybe we could even write this another way that we're more comfortable with here in calculus, and we could write this as dy dx. Okay, take a second, make sure that that's sinking in, and that's kind of making sense there. But this side, if we're going over 1, then the amount we're going up is the slope, which is the same thing as dy dx. So in this triangle, what we see is that b is actually dy dx. Okay, now we're getting somewhere. All right, so I'm gonna erase some of my work, just so that we can clean this up a little bit. Okay, so that is going to give us this little piece right there. Well, I don't want just that little piece. I want all of them, right? So here's what I'm going to do. I'm going to take the sum of all of those little pieces, right? The sum. So I'm going to take the sum of all of those pieces. All right, now that's good. So we know that integral sign is kind of fun to think of as an S for sum, because that's basically what we're doing with it. But we also know that integral is not just going to calculate those one unit wide pieces. It's going to calculate pieces that are very, very small and then add them all together. So if we are adding these things over and over and over again, and they're not just 1 unit apart. If they were 1 unit apart, that'd be fine, but we want this to be exact, right? We don't want this to be an estimate. So we're not going 1 unit apart. It's like we have to divide those up a little bit. So we need to, if we're going to add all those up, we want to add the small one, so we need to somehow make this unit right there, whatever that value is, we need to make that smaller. So we need to multiply it by something that's small, right? Because if you multiply 5 by 0.3, that's going to get smaller. Or if we multiply by 0.1, it's going to get much smaller. If we multiply 5 by 0.01, that's going to get much smaller. If we multiply that 5 into a very, 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 very teeny tiny change in the x, if we would make this a become very, 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 very small, how would we do that? Well, we would just have to multiply that by a very, very small number, dx. Okay? And that's it. That's our formula. That's how we're going to calculate the arc length of a curve. Okay, so going back, this part right there, that's just our a squared plus b squared equals c squared, because if we call a 1, then our b value is going to actually be the slope. Whatever the slope is, if we're going over 1, our b value is going to be the slope, so we can call that dy dx. So we have to take 1 squared, which is going to be 1, plus our slope dy dx squared, and then we have to take the square root of it. And then since we're summing all of them together, we're going to have to get it into a smaller part, and we've got to have that dx on there. All right, so let's use this formula and see if we can actually calculate some of these. So I want to know, what is the arc length of this curve from 0 to 1? So I've got this graphed here, and so I want to know, what is the length of this curve from there to there. All right, so let's use our formula that we know. Our formula is the integral of the square root of 1 plus dy dx squared dx. And that's going to be from 0 to 1. All right, so well, how are we going to find that dy dx? We're going to have to integrate this. So y equals 1 plus 6x to the 3 halves. Okay, so that would mean if we integrate this, dy is going to be, that one's just going to disappear. The derivative of 6x to the 3 halves, that's going to be 18 halves, so that's going to be 9x to the 1/2 dx. All right, so now to sub this in, we're going to need to know dy dx. So let's just divide the dx over, and we're going to have dy dx equals 9x to the 1/2. Okay, so let's do this. We've got the integral from 0 to 1 of 1 plus 9x to the 1/2 squared dx. Okay, so let's see what this is going to be. 9x to the 1/2 squared, that's going to be 81x. So we've got the square root of 1 plus 81x squared. 1 plus 81x squared dx from 0 to 1. I apologize. I got a little bit ahead of myself. That is just an 81x, not 81x squared. So, boy, looking at this, what are we going to do? What are we going to do here? Well, I don't like the way that's written. I struggle to see things when they're written with a radical sign. So I'm going to change this to an exponent. 1 plus 81x to the 1/2 power dx. And now I'm pretty comfortable integrating that. So 1/2, if we go up 1, this is going to be 1 plus 81x to the 3/2 power. And then to get rid of that 3/2, we'd need to have a, I'm going to erase this over here if that's all right, so that I have room to do this. To get rid of this, we're going to have to go getting rid of that chain rule, or the power. We need to go 2/3 out front. And then when we were integrating this, we would have had to take the derivative of that for the chain rule. So in order to get rid of that, we're also going to have a 1 over 81 out here. So the 2/3 to get rid of the exponent, and the 1 over 81 to get rid of that 81. And that's going to go from 0 to 1. All right, so now cleaning this up a little bit, this is going to be 2 over 243 times 1 plus 81x to the 3/2. All right, so when we put this into our calculator, let me see what this is going to actually be. So 1 plus 81 is going to be 82. So we'd have 2 times 243 times 82 to the 3/2 power. Okay, and then we'd have to subtract. When we put in 0 for x, that's just going to be 0. So this is going to be 1 to the 3/2 power, which is just 1. So let's see what this is going to be. 2 over 243 times 82 to the 3/2 power. Minus 1. And it looks like it's going to be about 6.1 units long. And as I'm looking at that, this goes from 1 up to about 7. It's pretty straight line. So yeah, I'm believing that. I'm believing that that is our answer, about 6.1. Okay, so as you can see, this is not going to be it's not going to be easy, but it's not something that we can't understand either. All right? I know you've got it. Good luck.